Okay, welcome. In this video I'll discuss electron viscosity, and I'll go through the electron momentum equation and then see how electron viscosity gives rise to hyperresistivity. And this is small but can be important in some cases. This is a slight preview of the electron momentum equation discussion later. So in a later video I'll go through in more detail all the different terms, and particularly the Hall terms, which are important as well. But here I'll just concentrate on the electron viscosity terms and how this turns into a resistive or hyperresistive term. So I'll start writing down the electron momentum equation. So here we're going to concentrate on this term here, which is the electron pressure tensor, and we're going to compare this to this, which is the force due to collisions. And this is what usually gives rise to the resistivity, while this is what's going to give the hyperresistivity through the electron viscosity. So the electron pressure equation, PE, so electron pressure is a matrix, so rank 2 tensor, and this we can write as a combination of a scalar electron pressure plus this electron stress tensor, and this is where this viscosity is going to come in. And here we've seen in a previous video that this has components which are parallel and perpendicular. So it has a parallel and perpendicular components. And in a previous video these were labelled eta 0 for the parallel and eta 1 for the perpendicular components. There are then other components for the gyroviscous terms. For now we're going to concentrate on the eta 1, so the perpendicular parts, because what we're looking to look at is the case where we have say very narrow current sheets. So if this is for example J parallel, and this is say radius, we might have a case where you have very narrow current layers, and if this is very small, a very small width, then these viscous effects can become important. But these are perpendicular to the magnetic field, so that, or at least the gradients are perpendicular. So the current is along the magnetic field and the gradients are across the field, and so we're looking at this perpendicular viscous terms. And these were, let's kind of order, so the eta 1 e, this coefficient, is, at least in Brzezinski, at least for now, we're going to make some approximations. So if you remember, the perpendicular viscosity has quite a complicated form, but it's essentially the gradients across the field, and so the gradient of the divergence of the stress tensor, the electron stress tensor, so with a minus sign on the right hand side of this equation, this we can approximate. So here we're just going to look at order of magnitudes as essentially a diffusion equation for the electron viscosity, electron velocity here. And so this is basically a diffusion equation. So if you have a very narrow current layer with very steep gradients, and this term can become important, even though typically this coefficient is small. Okay, we're going to compare this term to the resistive term, and so this term is the friction, which is what becomes the resistivity, and this R force, so friction force. So we're going to compare to the friction force. So it's typically the ion electron collisions. So this RE, which is basically has a parallel collision resistivity, then times N times J. So this depends on the difference between the electron ion velocities, because that's what the collisions are. If there's no difference in velocity, then there's no net friction force. But this also has a second term, which is the thermal force, which we're not really going to discuss here, but it's just here for completeness. So we have a thermal force, and this is quite interesting that it comes about because the collisions, the collision frequency goes down as the temperature goes up, and so if you have a gradient in temperature, the hot side has fewer collisions than the cold side, and so there's actually a force going from the cold side to the hot side due to the difference in collision frequency. And so this gives a force up the temperature gradient due to the thermal force. Okay, so we can compare this force eta with the eta parallel. This is the resistivity. and that's just given by Spitzer. So Spitzer harm formula, for example. And so then in the equations, here we're just dividing through by the mass and the density of the electrons. So and dividing through by this En factor here, just cancel out some of these n's. What we end up with is, so see what I've done here is neglect the d by dt term. So there's a derivative in time that I've neglected. Here I've just taken this equation here at the top, this momentum equation. I've divided through by En, and so the En factor in here cancels out. There's the stress tensor term as an En term here, and I've neglected this term here on the left hand side because it depends on the electron mass, and so it's typically small. So this term here depends on Me, which is small. So in a later video I'll come back and I'll look at these terms and explain what effect they have. But at the moment I just want to compare what this term looks like. This is eta 1e, this is the viscosity term. Here I've neglected the difference between the ion velocity, so I've assumed the ion velocities are 0. So for now I've assumed the Vi is roughly 0. And that lets us get from electron velocity to ion velocity fairly easily, just by again dividing through by En. So we just have that the J is roughly so minus EnVA. That's how to get from this J to the previous equation. So it gives a factor of En. Then we divide it through by En, so we have an E squared, N squared here. Okay, so then we can rewrite this term using the previous expression for eta 1e. And then this we can write just in terms of the parallel this here. So see here we have a cyclotron frequency, so this will turn into a electron mass, and we can rewrite this whole thing, this tau e as well. So we can take out the factor of eta parallel, and then this here we just have a cyclotron frequency. So we have the thermal speed, and this clearly gives a Lambda radius. So rho e squared. So everything else essentially cancels out. You have a factor of 0.5 and a factor of nearly 2, so these essentially cancel. And so all that's left is this rho e squared. So this is the electron gyro radius. And so these terms appear like this. So Ohm's law is modified. So usually this is a small term, so because the Lambda radius, electron Lambda radius is very small. So rho e is really much less than any typical length scale. So this term is small. So hyperresistive term, which is what this is. So this term here is it's hyperresistive because it depends on a gradient of a current rather than just the current itself. But it can be important in some cases. So first, if there's any kind of turbulence or fluctuations on the electron scale, then this could potentially also increase this term, this coefficient here, because this coefficient is just purely from collisions. So this is a minimum kind of level rather than a typical. So if there's any turbulence, this could be enhanced. Second is if you have any small scale structures, this can also become important. So if you have strongly forced reconnection where there's an external force which is creating a very large current sheets or very small scales, this potentially can become important, say in violent events. So it's been found to be important in things like Elm eruptions, where you have very violent, very short, kind of short timescales, and in these events, very small timescales can be created transiently, and so it can be important to keep these terms, even though they're usually small. And lastly, this term, even though it's small, is often kept in numerical simulations, because it's one way of trying to suppress grid scale or very small scale fluctuations or unphysical structures. And so even though it's small, when the solution is smooth, it can be very useful for controlling numerical noise, which tends to occur at the grid scale. And so it's a physical way of motivating why this term should be in there. Often terms like this are added just purely for numerical stability, but this provides some kind of a physical basis for including this term, or why it should be there. least at a small level.